In this video, we're going to talk about geometric sequences. In a geometric sequence, the ratio of any term, except the first one, to the previous term is constant for all pairs of consecutive terms. This constant or common ratio is represented by R. So for example, in the sequence 4, 8, 16, 32, etc., A is 4, just like in an arithmetic sequence, and R is 2 because we're always multiplying by 2 to get to the next term. If you need to find out the common ratio and you know that it's geometric, just divide term 2 divided by term 1, or term 3 divided by term 2, or term 4 divided by term 3, etc. So in that first case, A is 4 and R is 2. In the second case, A is -3 and R is -2. When you see a geometric sequence where the signs are alternating, that's a really good sign that you have a negative R value. In the next case, you see that A is 100 and we're always dividing by 10. Another way of saying that is we're multiplying by 1 over 10. So we could say A is 100 or R is 0.1. And finally, for this last geometric sequence, we've got a half, an eighth, 1 over 32. This should actually say 1 over 128, and this next one should actually say 1 over 512. A little typo there. But when you see that, you see A is a half and R is a quarter, because we're always multiplying by 1/4. Now, notice we can always evaluate R, as I said earlier, by dividing any term except the first one by the term before it. So in other words, R will always equal Tn over Tn minus 1. Obviously, n has to be greater than or equal to 2, and n will be a natural number. So the general term of an of a geometric sequence will always be given by this formula. So let's think about that for a second. Given this sequence right here, we know the first term is 4, and we know the second term is 4 times 2 to the exponent 1. We see the third term is 4 times 2 to the exponent 2. The fourth term is 4 times 2 to the exponent 3. So we see that the nth term will be 4 times 2 to the exponent n minus 1. And that's what we've written here. The first term is really AR to the 0. The second term is AR to the 1. The third term is AR squared. The fourth term is AR cubed. So what we've done there is kind of a casual establishing of the rule that Tn will always be equal to AR to the exponent n minus 1. Now, from the formula, we see that if R is greater than 1, the terms will increase, assuming, of course, that A is positive. If R is a number less than 1, but still positive, the terms will decrease if A is positive. And finally, if R is less than 0, the signs of the terms will alternate between positive and negative, because that's what happens when you keep multiplying by a negative number. So let's look at this first sequence. Is that geometric? Well, the way we're going to do it is simply divide term 2 divided by term 1, term 3 divided by term 2, term 4 divided by term 3. When we do that, we always get 3. So in other words, we're always multiplying by 3 to get from one term to the next. The common ratio is 3, and we have a geometric sequence. For this next sequence, it tells us that it is geometric, so we don't have to establish that it's geometric. So now that we know that it is geometric, it's easy for us to say A is equal to 5. R is just going to be whatever it takes to get from the first term to the second term. So we can just divide backwards. -15 over 5 is 3. Is -3. So we'll see right away that A is 5 and R is -3. And that's what we've shown here. And now, since we have a formula for the general term of a geometric sequence, we can use that formula and say Tn will be equal to 5 times -3 quantity to the exponent n minus 1, and there's our general term. The question then asks, what's the ninth term? So we sub in 9 for the n. N is always representing the ordinal position. We plug that in for n on the right side of the equation as well. And -3 quantity to the exponent 8 will be a positive number because the exponent is even. And the answer ultimately is 32,805. Now we'll do a similar process here. We see that the A value is 99. We're told that it's a geometric sequence, so it saves us a step of having to establish that. A is equal to 99. R is going to equal 1/3 because it's 33 divided by 99, or in other words, 11 divided by 33. So R is 1/3. So our general term is 99 times 1/3 to the exponent n minus 1. So we can actually simplify that. You'll notice here, it's not what I would specifically request on a test, but we see that 1/3 to the exponent n minus 1 can be thought of as 1/3 squared times 1/3 to the exponent n minus 3. And that's actually kind of interesting because 1/3 squared is 1/9, and 99 times 1/9 is an integer 11. And then we're still left with 1/3 to the exponent n minus 3. And so a lot of times you'll see it written this way, but just understand that this expression here and this expression here are actually equal expressions or equivalent expressions, and one of them just has a reduced integer, and sometimes people simplify it that way. Now, to find out what the 9th term of the sequence is, we'll use our original expression for Tn. We'll sub in a 9 for n, and we'll end up with 99 over 6,561. And of course, it goes without saying we should always reduce our fractions. The 9th term of the geometric sequence is 11 over 729. Now, what if we have a geometric sequence where the 8th term is 896 and the 10th term is 3,584? We'd like to determine the 15th term, and there's a bit of a warning here. It's a bit of a trick question. Well, what we do, not really a trick, that's a bad way of putting it, but we see that we know the formula Tn equals AR to the n minus 1, so that means if we let n be 8, T8 will be AR to the 7. And since T8 is 896, that means 896 is equal to AR to the exponent 7. Okay, cool. Now similarly, since Tn equals AR to the n minus 1, that means T10 will equal AR to the 9. Well, since T10 is 3,584, that means 3,584 will equal AR to the exponent 9. All right, so we have these two equations. 3,584 equals AR to the exponent 9. 896 equals AR to the exponent 7. Well, we're going to solve this by dividing. We're going to divide both sides of equation 2 by the appropriate side of equation 1. So 3,584 divided by 896. And on the other side, AR to the 9 divided by AR to the 7. We're allowed to do that because we're dividing both sides of an equation by an equivalent amount. What we end up getting there is that 4 equals R squared. And a lot of times what happens here is students will right away say, okay, that means R is 2. But for all we know, R could be -2 as well. So we have to consider that. So 4 is equal to R squared, meaning plus or minus the square root of 4 equals R. So R is equal to plus or minus 2. That's why we're saying it's kind of a trick question. So in case 1, if R is equal to 2, then we end up with A equaling 7, because A times 2 to the 7 will equal 896. 128A equals 896, A is 7. But in the case that R equals -2, we ultimately get -2 quantity to the 7 times A equals 896, meaning -128A equals 896, meaning A equals -7. So we have a case where A is 7 and R is 2, and the 15th term is 114,688. And we have another case where A is 7 and R, this should say, sorry, A is -7 and R is -2. Sorry about that, little typo. A is -7, R is -2. And when you plug that in, the answer is actually correct, as you see there, negative 114,688. Negative 2 raised to an even exponent, ultimately the exponent is 14, makes negative 2 quantity to the 14 positive, but we're multiplying it by negative 7, which means we're getting an answer of negative 114,688. Okay, so basically, ignore that little typo if you could. I mean, I should have had a negative sign there, but we see everything else on the board is correct. And the 15th term of the sequence should either be 114,688 or negative 114,688. Now, what if we wanted to determine the first 5 terms of the sequence shown? Okay, well, what we would do is simply let n equal 1, let n equal 2, let n equal 3, let n equal 4, and let n equal 5. And we would use BEDMAS and evaluate, and we would get that the first 5 terms of that sequence are 6, 8, 14, 32, and 86. Now, we'd like to know next if that's actually a geometric sequence. The answer is no. But we have the first 5 terms there. Now what we're going to do is see what do we have to multiply to get from 6 to 8, and what do we have to multiply to get from 8 to 14. In other words, we're going to divide 8 divided by 6 and 14 divided by 8. We see when we do that, we don't get the same value. We don't have a common ratio. So this is not a geometric sequence.